So there's this thing called gravity that pulls us down to the Earth and also guarantees that our planet doesn't fly away into the deep interstellar void of a galaxy. This is the force that keeps the moon going around the Earth and prevents us from floating around everywhere like these guys on the Vomit Comet floating around in microgravity. So why can't we throw footballs as far as we want? Why does this effect even exist? To answer this, we'll take a look at a brilliant physicist born in 1642 named Sir Isaac Newton. It all started in 1666 when Newton most likely observed an apple falling from a tree and not his head as myth would dictate. After many years of research on not only gravity but also the origin of light and casually discovering calculus along the way, he finally publishes his major work Principia. This 3-volume book details the 3 laws of motion he discovered, as well as the one that is most important to us, the law of universal gravitation. Side note here, Robert Hooke was another scientist from Newton's time, and although he did make a lot of contributions to what we know today in science, he claimed that Newton had stolen the idea of the inverse square law from him in his works, but this claim has been dismissed since Newton was the first to actually mention the concept of a force of gravitation increasing exponentially as two objects got closer and closer. The formula itself is pretty simple. You simply take the product of the two masses in question, divide them by the square of the separation, and multiply them by a certain constant g. Of course, all of this is in SI units. The law itself states that a particle attracts every other particle in the universe using a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. What this means is that you, your cat, the moon, and that galaxy are all attracted to each other by some force, irregardless of how far they are from each other. How crazy is that? Let's take an example. Say we have two masses, mass m1, which is 15 kilograms, and mass m2 of 10 kilograms, and they're both separated by, say, 2 meters. So to find the force between them, we simply substitute all the variables in the formula, and in the end multiply them by g, which is the gravitational constant, which is found experimentally. The value of g is this. In the end, we come up with an answer of about 2.50 times 10 to the minus 9 newtons, 236 figs, of course. If we double the mass of a mass m2 to 20 kilograms, and keep them at the same distance, then using the formula, the force that is exerted is twice as much as the original. If we divide the distance between the two same objects by 2 and use the formula again, what we find is that the force is exactly 4 times greater than our previous result. This is an example of the inverse square law. What's interesting about our result is that the forces are extremely small. What this tells us about gravity is that it needs extremely large objects in order to have any substantial effect, for example between the Earth and the Sun. Now, irregardless of how the objects are placed next to each other, they'll always exert equal and opposite forces, meaning that they'll always have an acceleration towards each other. Since the formula only concerns particles with mass, then we'd expect something like light to not be affected by gravity, but instead, what we find is that light curves around massive objects like galaxies, giving us the effect of gravitational lensing. Wait, this doesn't make sense. So how can an object with no mass be affected by gravity? To figure this out, we'll turn to Albert Einstein and the most famous physics equation of all, E equals mc squared. This relates mass and energy, and tells us how much energy is emitted when mass is converted. When we use the energy of a photon with the equation, we find that the path the photon takes is not exactly the one that is observed. So what causes this discrepancy? Once again, Einstein saves the day with his laws of general and special relativity. He describes space as a sort of mesh, combining space and time, where any object with mass exerts stress on it. Naturally, objects with higher mass exert more of a stress on what he calls the space-time curvature. Simply put, a photon will exert some sort of contribution to what we call the electromagnetic stress-energy tensor, which can be described using this interesting equation. What this means is that a photon will exert stress on the flow of energy and momentum in spacetime, which simply means that it will be affected by objects which also have mass as well. So as you see, this formula is not exactly perfect. However, it is very useful in terms of determining orbits around stars, and is useful in calculating how exactly we should send satellites and probes to different planets. The science of figuring out the sum of the different forces and the accelerations of celestial objects is what we call the n-body problem. The n-body problem revolves around predicting individual motions of group of celestial objects. There are two main subsets, the two-body problem and the restricted three-body problem. The two-body problem consists of predicting the motion of two different objects. This was solved by Johann Bernoulli using classical theory and not by Newton. The idea behind the problem is that the two objects will have two different equations to describe the net force that is acting on them. They are in vector notation and so aren't equal. A major consideration that Newton did not take into account when formulating his equation was that in the case of an orbit, the two objects will accelerate towards each other and therefore will orbit what we call the barycenter, which is the center of mass of the whole system. The equation for the two-body problem itself looks slightly different than our original formula. We use the vector position of the two masses, and instead of squaring them, we use the cube of the separation. The general formulation, which applies for any number of bodies in a system, basically describes the net force that one object will exert on the other. Notice that we still use the gravitational constant and the magnitude of the distance between the 2 points. This is of course because the position vectors are in 3D and we only need the magnitude. And logically, if we add all the forces over all the masses, we yield the equation of motion. This equation of motion can be summarized in this form. This formula basically describes every single force that every single object in the system exerts on every other object. Notice that U stands for the self-potential energy of the whole system. But what makes this formula very interesting is that to understand its full significance, you have to take into account a bunch of other equations which have their own backstory. All in all, you have to take into account kinetic energy, momentum, and the center of mass, for example. But that's not all. You still have to take into account equations which describe different things, for example those for the total angular momentum and the moment of inertia of a system. So this law is very useful as well. This is only one out of many problems in which we can apply the law of universal gravitation. In conclusion, the law of universal gravitation helped us reveal a lot about physics. For example, calculating the acceleration of falling objects on Earth, calculating the orbits of planets and satellites in space, and the path needed in order for us to meet different planets. And also in physics, where we need to calculate the net force of a whole system and the acceleration. And of course, it revealed to us the inverse square law, which is a trend that Newton discovered and is paramount in understanding this law. Unfortunately, this did not come without any conflicts, but today we know who discovered it. But there are still a lot of questions that need to be answered about gravity. Throughout all his works and calculations, Newton never found out the reason as to why gravity is a phenomenon that exists. And this is something that we are still trying to find the answer for to this day.
Let me holler at the DJ. Come on, DJ, put the record on the replay. Don't you see how them bitches move their booty? Every time you play this record, smell like cash too. Follow them, screaming like a coupe. Misdemeanor, move my dick like a hoochie. But I'm haters, whatever.